Hi everyone, I'm Michelle. Welcome to my video. Today we are diving into our first supervised learning model. If you remember, supervised learning can be split into two major branches, classification and regression. In today's video, we will focus on the simplest form of regression, linear regression with one variable. Linear regression might seem simple at first glance, but it's a powerful tool that lays the foundation for understanding much more complex models. By starting with the basics, we will build a strong understanding step by step. Think of this as setting up the cornerstone of a much larger structure. Let's start by discussing the purpose of supervised learning and regression problems. In supervised learning, as we have mentioned before, we feed data into a model and we expect the model to provide the correct answer. For regression model specifically, the output is a continuous value, meaning it can take on any value within a range. For example, it could predict real-world quantities like house prices or a person's height. The goal of a regression model is to predict these real-world values as accurately as possible. Isn't it fascinating how this simple concept applies to so many different fields? From price houses to predicting the future trends, regression models have the practical uses everywhere. Let's use a common example, the house price prediction from Kaggle. First, I will walk you through the general process of building a regression model, and then we will get into the details. To start, you will need a dataset containing information about houses and their prices. Imagine you collect data points like the ones shown on this slide, then plot them on a graph where the x-axis represents the house size and the y-axis represents the price. Visualization is always an exciting step. It transforms the raw numbers into the patterns that are easier to understand. Here, we're using it to start uncovering the relationship between the size and the price. Our goal is to use this dataset to train a model that can predict the prices as accurately as possible. The model's task is to find a line, represented in green here, that minimizes the average error between the predicted values and the actual data points. While the line won't match every point perfectly, the goal is to minimize the overall error. I always think of this step like trying to draw a smooth path through a set of scattered points. It might not be perfect, but the better it fits, the closer we get accurate predictions. Once the model is trained, we can use it for predictions. For example, if we have a new house with a size of 1,899 square feet, we can use the model to estimate its price. Let's say it predicts around $479,000. Even though there might be some deviations from the actual price, if the model fits the training data well, the prediction should be close to the real value. It's incredible how just a bit of math and data can help us make educated guesses about something as significant as a housing price. It really highlights the practical power of machine learning. Now let's dive into the details of linear regression with one variable. First, let's go through some notations. M represents the number of training examples or the number of the rows in your dataset. X represents the input feature, for example, house size. Y represents the target variables, for example, the house price. And each pair of X and Y is a training example. Individual examples are denoted with a superscript. For instance, X of I, if that is X of 1 for the first input and Y of 6 for the sixth target. So understanding all these notations might feel like learning a new language, but once you master them, everything starts making sense, and you will feel much more confident analyzing the data sets. Okay, let's try a quick example. On this slide, there is a table showing the house sizes and prices. Can you identify which value correspond to X of 1 and Y of 6? Take your time to think this through. This type of exercise may seem like simple, but they are key to understanding the mechanics of how data is handled in machine learning. Okay, ready? The answer is highlighted in the red. So x of 1 equals to 2104 and y of 6 is equal to 302. I believe you already got it, right? So great job. If not, don't worry. This is a learning process and we are just getting started. Keep practicing and it will all click soon enough. Now that we are familiar with annotations, let's discuss the process. First, we start with a training dataset. This dataset acts as the foundation for our entire model. It's like the ingredients in a recipe. The quality of your output depending on the dataset you start with. Next, we feed this dataset into a learning algorithms. This is where the magic happens. The algorithms process the data and start uncovering patterns, turning input into the meaningful insights. Think of it as a detective piecing together clues from evidences. The learning algorithm job is to output a function. In this case, the function predicts house prices based on the input data. Sometimes we refer to this function as a hypothesis. It's like a crystal ball for your data. Once trained, it helps us predict future outcomes with surprising accuracy. The hypothesis takes an input like a house's size and the outputs an estimated price. The simple process forms the basic for all the supervised learning models. You might wonder why focus on something so basic. The answer is that these core ideas are building blocks. Once you understand them, you can tackle more complex problems with ease. It's all about mastering the foundations. So let's now navigate and see how do we represent h of x. In linear regression, the hypothesis is represented as h of x equals to theta 0 plus theta 1x. Here, theta 0 and theta 1 are the model parameters. X is the input, for example, the house's size, and h of x is the predicted price. For this video, we will focus on models just with one variable. Notice how this formula is simple yet powerful. It's just like drawing a straight line in a math class, but now it's being used to predict real-world outcomes. Then the next question would be, how do we find the best hypothesis? The key is to adjusting the parameters theta 0 and theta 1 to minimize the errors between the predicted and the actual values. Think of the hypothesis as a straight line, and the value of theta 0 and theta 1 determine the positions and the slope of the line. Adjusting these values helps the line better fit the data points. This part of the process feels a bit like sculpting. You keep refining the shape until it looks just right. So the ideal scenario is to adjust and select the values of theta 0 and theta 1 in such a way that the hypothesis aligns as closely as possible with all the training examples. But this raises another question. How do we measure the relationship between the hypothesis predictions and the actual values? This is where we introduce a method to measure the performance of our hypothesis functions, called as the cost function. The cost function works by calculating the average differences between the hypothesis predictions and the actual values. However, the differences is squared to emphasize the larger errors and create more robust measurements. This means the cost function represents a more advanced version of an average differences. Here is how we calculate it. First, take the square difference for all the data points, and then we sum them up, divided by the total number of the samples m. You might also notice that in the formula there is a 1/2 factor. This is added to simplify the calculation of gradient descent later too. We will discuss gradient descent in details in the future sessions. Now, at this point, you might be thinking, this formula looks so familiar, and you are absolutely right. This is what we previously introduced as a key metric for measuring model performance, the mean square error, MSE. If you have forgotten what MSE is, feel free to revisit our earlier video. I will include a link in the description box below, so you can check it out. Let's use a simple example to understand the cost function better. Suppose we have a dataset and a hypothesis function as shown on this slide. The yellow dots represent the actual data points with house size and prices, while the green line represents the hypothesis function. Looking at this pie graph, you can see that the green line passes through the original 0, 0, and the slope up forward to fit the data points as best as possible. Based on this, we can assume the optimal theta 0 is 0. Why? Because when x equals to 0, the hypothesis result is also 0, meaning theta 0 is equals to 0. Next, we calculate theta 1. Let's assume theta 1 equals to 1. If every point perfectly matches the actual values when plugged into the hypothesis functions, the cost function value will be 0. We can plot this scenario on the graph, where the green across represent the cost function value when theta 1 equals to 1 and j of theta equals to 0. But in most of cases, we cannot immediately find the optimal points where the cost is minimized. So how do we get there? To find the best theta 1, we need to iteratively adjust its value and calculate the cost function result. For example, if we set theta 1 equals to 0.5 and plug into the hypothesis functions, we calculate j of theta equals to 0.58. We can then plot this value as result on the graph, showing theta 1 equals to 0.5 and j of theta equals to 0.58. This is just one data point. When we're repeating this process, gradually adjusting theta 1, we can create a complete picture of how j of theta changes with different theta 1 values. By continuing this approach, adjusting theta 1, calculating the cost plot and plotting the result, we can eventually generate a graph like the one shown on this slide. Here, each point represents a specific theta 1 value and a corresponding cost function result. Now here is the key insight. A good model minimizes the prediction errors, which means the cost function value should be as small as possible. In our example, the yellow dot on the graph marks the global minimum cost. This happens when theta 1 equals to 1, giving us the best hypothesis and the lowest cost function values. So far we discussed the scenario where theta 0 is equals to 0, which is fixed. But what if we need to adjusting both theta 0 and theta 1 to find the optimal solutions? In this case, we still use the cost function, but the relationship between the parameters and the cost function is now visualized in a 3D graph. As shown on this slide, the x and y-axis represent theta 0 and theta 1, while the z-axis represent the cost functions. Our goal is to find the lowest point on this surface, so that is the global minimum. Using tools like MATLAB, we can visualize this process and see how adjustment to both parameters bring us closer to the ideal models. This ensures our hypothesis achieves the lowest possible cost function values. For the last part of this video, I would like to introduce our YouTube membership. As we mentioned earlier, for the machine learning whole series, we're going to share some Q&A pairs on each paragraph, which will help you get a better understanding of machine learning itself and prepare for the interview questions. For all the Q&A pairs, we are going to list the videos on the YouTube channel membership. If you are interested in these questions, please follow us step by step and join our membership. To join as our membership, please first click on our channel name. You can find it under any of my videos. After clicking on the channel name, you should be able to navigate to our main channel page. From there, on the right side top, there is a join button. Click on the join button and there will be a pop-up window. Please notice that we have 3 different kinds of memberships, only one for English version and the other 2 are for Chinese version. If you only want to see the English version videos, please make sure you choose one named as with English. Once you choose this category, on the right side there will be a pop-up window and then you can click on the join button. After finish all the steps YouTube requires, you are officially one of our membership. Congratulations! If this is your very first time to watch my videos, please do not hesitate to subscribe my channel and give me a thumb up. I will keep posting nice videos for you and study with you together all the time. Okay, that's all for my videos today. Thanks for watching and have a great day. See you in my next videos.